Alright, so we are looking at problem 2.47 from Mastering Physics. The problem is this. You're driving down the highway late one night at 20 meters per second when a deer steps onto the road 35 meters in front of you. Your reaction time before stepping on the brakes is 0.5 seconds. The maximum deceleration of your car is 10 meters per second squared. The two questions we'll answer are, how much distance is between you and the deer when you come to a stop? And also, what's the maximum speed you could have and still not hit the deer? So I'll show you what I've done so far. I've drawn a diagram indicating three positions of interest. So first, initially I'm going to label the first point x naught, v naught, t naught. So this is where the problem starts. That's our origin. I'm going to label an x point, x1, t1, and v1. That between these 2 points, the car's traveling and half a second goes by without braking. Then we apply the brakes, then the car slows down. So between x1 and x2, that's when the car is slowing down, and it finally comes to a stop, hopefully in front of the deer. We've defined moving to the right to be the positive direction. You should always do that. Decide what your positive direction is going to be. The next thing we'll do is define a motion diagram. So here you see the car moves with constant velocity for half a second. At this point, it starts braking, and finally comes to a stop. Hopefully, again, in front of the deer. The next thing we'll do is we'll label our knowns and unknowns. So what do we know? Well, we picked the initial point to be the origin, so that will be our 0. They didn't tell us that, but that makes good sense. Set your origin at the initial point of the problem, call it 0 meters. The same with time. Start your stopwatch at that initial point, call it 0 seconds. We also know the initial velocity, v naught, is 20 meters per second in the positive direction. We know the time between t naught and t1 is 0.5 seconds. We also know that v1 and v naught are equal. That, again, going back to the motion diagram, so v1 and v naught are equal. Going back to the motion diagram, that half a second goes between the initial point and the first point there, and there's no braking. So v1 and v naught are equal. We know that once the braking starts at point 1, you get an acceleration of negative 10 meters per second squared. And again, the car is slowing down. If the car is moving in the positive direction, slowing down means there's a negative acceleration. We also know the car finally comes to a stop at point 2, call that 0 meters per second. We know the position of the deer is 35 meters. So what are our unknowns? What are we looking for? We want to know the position where the car does stop. Okay. We have two portions to consider here. That there's a first portion where the acceleration is equal to 0. So when the acceleration is equal to 0, that happens between points, the initial point and the first point. So what we do is we look for a kinematic equation that involves the things that we know and the one thing that we don't know that we want to solve for. So we don't actually know where the car starts to brake. So we don't know that point. So let's solve for that point, x1. So looking at those kinematic equations, x1 equals x naught plus v naught delta t. Again, how do I pick that equation? Well, I'm looking at the interval between the initial and the first point, and I want to know what the position is at the first point, because I want to eventually know what the position is at the second point. So, do I know x naught? Yes, I do. In fact, it's 0, so go ahead and get rid of that right away. Do I know v naught? Yes, I do. Do I know the time between those 2 points? We'll call that delta t, the change in time from 0 to 1, just to be clear. If I plug in all the values, I get 20 meters per second times 0.5 seconds. And notice the units cancel. Meters per second times seconds gives you meters. So that's 10 meters. So the car travels 10 meters between those 2 points. Now let's consider the second interval. So when the acceleration is equal to negative 10 meters per second squared, what we'd like to know is that final position, right? We want to know what x2 is. So if I look again for an equation that involves the things that I know and the one thing that I'd like to solve for, I would like to solve for x2. I don't know the time between these 2 points, so I can't use an equation that involves the time. If I refer to my equations, the equation that I'm going to pick relates the velocity between the 2 points, because I do know those quantities. I do know the acceleration. And then the change in position is really what I'm looking for. Change in position from 1 to 2. Because I already know that the change in position between 0 and 1 is 10 meters. So now if I just solve this equation algebraically, let's see, if I move v1 over to the other side, now solve for delta x1, 2. Just divide both sides by twice the acceleration. Okay, so now I have an expression for the change in position between 1 and 2. So plug in what I know. The final velocity at the last position, position 2, is 0. Make sure you keep that minus sign though. Minus v1 squared. V1 squared is the same as the initial velocity, remember? And the initial velocity is 20 meters per second. Make sure to square it, and then divide by 2 times the acceleration, which is negative 10 meters per second squared, because we're slowing down. Really important to keep the minus in there. You can see because the minuses have to cancel each other, otherwise you get a negative for the change in position, and that wouldn't make sense. So if you plug in and solve, and notice the units will cancel, you get meters squared, seconds squared on top. You have meters in the bottom, and the meters will cancel one of the meters, and then you have seconds squared in the denominator of the denominator. So the seconds will cancel and you'll get meters. So if you do the math, you get meters. Overall, if we solve for the first displacement was 10 meters. If the second displacement is 20 meters, the total displacement is equal to 10 plus 20, which is equal to 30 meters. So, where do we stop? We stop 5 meters in front of the deer.